Okay, so in the rest of the talk, I want to give a number of examples of recent and ongoing work, which basically add more instances of sequences of errors like this. Except that in this case, we're really learning new things about quantum field theory. Of course, historically, the second law of thermodynamics was already known, so maybe this would not have been such an impressive story. But you can see that it's a powerful method if you can get something like the second law from it. And these new results really are instances where we're discovering very interesting properties of quantum field theory through this method. Okay, so in order to go further, we have to develop a few more mathematical notions that are all related to this basic idea of replacing the area with a quantum-corrected area or the entropy with a generalized entropy. And just taking that a little bit further, one notion that's closely tied to area and general relativity is the notion of classical expansion. So the classical expansion is associated with, you have some surface in let's say, two-dimensional spatial surface, a clonal surface in 3+1 dimensions, and you've got some light rays orthogonally coming out of that surface, and so they might be moving apart, they might be moving together. If they're moving together, if the cross-sectional area spanned by these light rays is getting smaller, then the expansion is negative. So more precisely, the expansion is defined as the rate of change of an infinitesimal area element carried along the congruence of light rays per unit area, along some affine parameter. Okay. All right, so what we'd like to have, is a quantum generalization of this notion as well. Okay, and in order to do that, I'd first like to give you a more sort of needlessly elaborate definition of the classical expansion. So let me again draw a surface like this. This time I'll draw the whole surface, and then here's some light rays that are coming out of that surface, and here's some deformation I have, some area element that's shrinking or expanding or doing something. Instead of just worrying about the area change of this area element from here to here, I could worry about the change of the area of the entire surface. And since I'm taking the derivative, it wouldn't make any difference because this part is just constant. Right? So I could really think of this as a functional derivative. Where v of y specifies the position of this surface along a congruence of light rays, and I'm going to vary this at one place. Let's call that place y1. And I'm going to ask how does the area of the whole surface change under such a variation, and I have to put 1 over the square root of the induced metric here to make everything work out. Okay. The reason that I'm changing to this funny functional derivative notation and sort of carrying along this whole inner piece of the surface is that that's the version that generalizes easily to the quantum expansion. So the quantum expansion can then simply be defined as this. Now I can just replace area with generalized entropy. If I didn't have a whole Cauchy-splitting two-dimensional surface here, then it wouldn't be clear what the entropy on the outside is. And particularly the entropy on the outside depends on what the surface is doing in places that I'm not deforming. And so this is my starting point. But that's the quantum expansion. And this concept, to my knowledge, was first introduced by Aaron Wall. And for example, one thing he was able to do with it is prove a new sort of pinhole singularity theorem for surfaces which are quantum trapped, in other words, which have satisfied the quantum expansion analog of a trapped surface. And he was able to show, assuming the generalized second law, he was able to show for those surfaces that there has to be a singularity in the future. So yeah, I should maybe set that a little more clearly. So suppose I have some congruence of light rays. I want to specify the surface sigma that already appeared on this drawing in terms of where it lies on those light rays. And so I can just imagine that the transverse direction is some bunch of variables y, and I can specify some function v of y that tells me where the surface lies, and then the deformation can be expressed as a variation of that function. Thank you. All right. So here, that's why I want to stress these notions, for example, of classically trapped. So classically trapped, right, means that I have some surface that we suppress all of its spatial dimensions and just draw the two light-like congruences orthogonal to it, and let's call this the k congruence, and let's call this vector here L. And if theta k is equal to 0, and theta L is everywhere less than 0, then we call this a marginally trapped surface, for example, right? And so it's now very easy to generalize and introduce concepts like marginally quantum trapped, and so on. Okay. All right. So I wanted to give you the next example of a structure like this, where we start with GR, make a hypothesis about a quantum-corrected statement in semi-classical gravity, and then obtain a result of quantum field theory. And the GR result that I want to start with now is the focusing theorem. So my diagram now is going to look like this. It's a very dumbed-down version of the focusing theorem, actually. So we're going to take the classical statement that light rays are always focused by matter. I don't know if can you read this down here? Can anybody not? Down here, I should ask. Okay, so this is a prime here. What this means is that if light rays encounter some matter, they tend to get focused. Let's say they're parallel to start with, so theta would be 0, and then they encounter some matter, and then theta goes negative. What doesn't happen is that light rays get sort of made to expand by encountering matter, so long as the matter has positive null energy, or 0. Okay, so this is a classical statement. In fact, classically you can make stronger statements than this, but this is the one that we know how to generalize. Okay, so this is work with Aaron Wall and Stefan Leichenauer and Jackson Culler and Zach Fisher. I think that's, my students can correct me if I'm getting it. Okay, so that's the classical statement that we started with. Again, this assumes the null energy condition. If the null energy condition is violated, such as near a horizon of a black hole, then this statement does not hold. And near the horizon of a black hole, you have null congruences which do precisely this anti-focusing thing. And so it's pretty obvious what we're going to do here. We're going to conjecture that big theta prime is always less than or equal to 0. This is the quantum focusing non-theorem. I should say that, even though I wrote theorem up here. It's also not a theorem. It's a conjecture. This is a guess about quantum gravity. We think that once you include order GH bar corrections, this statement still holds even though this one fails. Okay. Get rid of this. Now this notation is a little bit imprecise. This theta already is a functional derivative, if I'm being careful. And how I write this down, this big theta is a functional derivative, the generalized entropy. And then by big theta prime, I really mean a second functional derivative. So I have to put, another dv y2 or whatever down here. And so when I have a second functional derivative, there's really an important difference between whether I'm varying twice at the same point, like so, or I'm varying twice at two different points, where y1 is not equal to y2. If you vary twice at the same point, the answer that you get has a delta function that you will usually want to strip off if you're interested in the prefactor, and if it's at different points, it does not. Okay. But another way of stating what theta is, you guys can ask later if you want more clarification on that. All right, so this is the statement. In other words, there's some combination of the behavior of the area spanned by the light rays and the entropy of the matter outside of the surface that's spanned by the light rays. And it's that combination that satisfies some sort of negativity, not each term separately. So maybe I should write down a couple more formulas just for sort of developing some intuition. So theta, of course, can be expanded back out as like so. And if I don't like these functional derivatives, then we just pick a fixed tiny little area element, A, like maybe the size, and then just deform that one and think of that as an ordinary derivative. And then take a limit where that goes to 0, which I haven't written down. Okay.
So this thing about whether you vary in the same place or different, right?
Yeah.
When you write the capital theta prime,
I mean, I don't care how you do it.
Okay.
Yeah, so it should hold either way. Now, it turns out that when you vary at two different places, the quantum focusing conjecture actually is a theorem because it follows from strong subjectivity. Okay, so to the extent that it's a non-trivial hypothesis, it's the diagonal part that's the most interesting one. Okay, good. So this could be done in very general spacetimes, but now we're interested in taking a limit in which this hypothesis reduces to a statement that just has h bar in it and no longer G Newton, a statement just about quantum field theory. And the way that you can obtain this limit is to consider, there's more general ways of doing it, and Stefan wrote, with a bunch of my students wrote a very nice paper about exactly how general, but for the purpose of this talk, let's just specialize to a null plane in Minkowski space. We're very often interested in quantum field theory in Minkowski space, so some surface of performance equals t, for example, kind of like this. Okay, and then along this null plane we have vanishing classical expansion. Well, the classical expansion will pick up terms of order GH bar if we include quantum corrections due to focusing by the quantum matter. So we can compute those deterministically. Okay. And so in this limit, we can expand the quantum focusing conjecture as follows. So here's just a restatement of the quantum focusing conjecture. And now we expand this out like so. Sorry, this theta comes from the derivative of 1 over the area element, so that picks up the theta here. And that should probably be an S1 prime, sorry. And then we can use Rachel Riley's equation here. And I'm already going to forget about this term, because big theta is at most order GH bar. Classically it's 0 for this surface, and then it could pick up a correction of order GH bar, but then there's another GH bar in front here, so this is going to be high order, and we won't worry about it. Okay, and then now we're just going to expand this term using Rachel Riley's equation, which looks like this. We get minus half theta squared minus the shear squared. This should really have two indices, but I don't want to clutter things too much. Minus 8 pi g times the tensor expectation value along the congruence. Plus, again, this term. And I'm going to drop this one here, so we're going to get 4 GH bar over A SL double prime. Okay, now we can drop some more terms because there's also no shear here, and there's, again, this is again at most order GH bar squared. So these terms will not be important. And so now I have the statement that these two terms together are less than or equal to 0, which I can restate as what is called a quantum null energy condition. Let me maybe write this out explicitly this time as a limit as some cross-sectional area goes to 0. In other words, the local stress tensor twice contracted with a null vector at any point is, whoops, this should be an inequality, is greater than or equal to 0 according to the null energy condition. The reason we call this the quantum null energy condition is that this is the quantum correction to the null energy condition. It has its bar in front of it. And what now forms the lower bound for the local stress tensor is this non-local quantity, the second derivative of the phenomenon entropy on one side of the surface that on one side of the cut of this null plane that I'm considering under these variations. But any questions about this statement? So that's the Q quantum null energy condition. Okay, so there are a couple of things that I should say about the quantum null energy condition. Unlike to say that this is not a statement we don't care about. It's of great interest to have a lower bound on the local stress tensor. It was known for a long time that there could not really be such a lower bound as a local statement. Here, what get around that is to integrate the local stress tensor over whole light ray, a null line, and then say that that's the average null energy condition. That we posit. Here we treat the non-locality on the other side. This von Neumann entropy, of course, depends not just on the surface at the place where you deform it, but on the surface far away as well, and on the entropy of matter far from the surface. In any case, it's a new statement in quantum field theory, and since it doesn't have Newton's constant. It's a new statement in quantum field theory, and since it doesn't have Newton's constant in it, we can hope to prove it within quantum field theory. And so such proofs were found. We gave one in our paper for free quantum field theory. And I want to stress that while it took me one line to derive this from the quantum focusing conjecture, it takes you like 25 pages of pretty dense